Why do critical points have to include places where the function fails to be differentiable? Here's a specific example that we can work through to see why it's necessary to check points of non-differentiability. You'll notice that I've included some absolute value brackets to introduce some non-differentiability. Okay, anyway, here's the problem. Find maximum and minimum values of this function, x minus the absolute value of x squared minus 2x, and do it on the interval between 0 and 3. Well, how do I proceed? Let's differentiate. Okay, so I differentiate. F prime is, well, the derivative of x is 1 minus the derivative. Okay, whoa, wait, what am I going to do about differentiating this absolute value? I can rewrite this function as a piecewise function, getting rid of the absolute value. So here's the original function, right? It's got an absolute value. And remember what absolute value does. Absolute value negates its input if the input's negative, right? So the absolute value guarantees that its output is positive, but with the same magnitude as the original input. So all I got to do to rewrite f as a piecewise function is to deal with that, right? I've just got to make sure that if this input is negative, then I better flip the sign, the SIGN, of the absolute value. Now, I want to know the derivative of this function, and I can compute that by just differentiating each piece in my piecewise defined function. So here I go. I'm going to differentiate these two pieces separately. So the derivative of f is also now a piecewise function, and I should differentiate this. The derivative of x is 1 minus the derivative of this, which is 2x. That's the derivative of x squared, and the derivative of 2x is just 2. And this is if x squared minus 2x is bigger than 0. And the derivative of this is 1 plus the derivative of this, which is 2x minus 2. And this is if x squared minus 2x is less than 0. And you'll notice that I'm careful to change the greater than or equal to here to just greater than. And the reason is because this derivative is not going to be defined when this quantity is equal to 0. Now it is time to hunt for critical points. Now, to simplify our hunt for the critical points, I can rewrite f prime a little bit to make it a little bit easier to see what's going on. So what can we do here? Well, 1 minus 2x minus 2, that's the same thing as 3 minus 2x. And 1 plus 2x minus 2, that's the same thing as minus 1 plus 2x. All right, and then I can rewrite this x squared minus 2x greater than 0 and x squared minus 2x less than 0. To say that x squared minus 2x is bigger than 0 is the same as saying that x is less than 0 or x is bigger than 2. And to say that this is less than 0 is just to say that x is trapped between 0 and 2. All right, now that I've got this nicer way of writing the derivative, I can very visibly see that something terrible is happening when x is equal to 2. Because if this thing were differentiable there, you'd expect this quantity and this quantity to agree when x equals 2. But these things disagree when x is equal to 2. All right, so this function ends up not being differentiable at 2. Where is this thing equal to 0? Well, 3 minus 2x would vanish if x were 3 halves, but 3 halves doesn't satisfy this. So this first thing never results in a critical point where the derivative vanishes. What about this? What about minus 1 plus 2x? Well, this is equal to 0 if x is equal to a half, and that is in this region. So here's what we know. The derivative is equal to 0 if x is equal to a half, and the function's not differentiable when x is equal to 2. Well, the function's also not differentiable when x is equal to 0, but remember the endpoints of our interval that we're considering are 0 and 3. So if you like, you can include 0 as a point of non-differentiability, but it's in this list of endpoints, so we're going to have to consider it anyhow. Note that there's something really special in this particular example. I really want to emphasize that 2 is a critical point, not because the derivative is equal to 0, but because the function is not differentiable at the point 2. So to finish off this problem, to find the minimum and maximum values of my function f, all I have to do is check the critical points and the endpoints. So here's our endpoints, 0 and 3, a place where the derivative vanishes when x is equal to a half, and a place where the derivative is not defined when x is equal to 2. Now remember what the original function is? Right? F of x is x minus the absolute value of x squared minus 2x. So what do we get when I plug in 0? I just get 0. And when I plug in 3, I also get 0, right? 3 minus, well, 3 squared is 9 minus 2 times 3. That's 9 minus 6. That's 3. 3 minus 3 is also 0. When I plug in 1/2, I get minus a quarter. And when I plug in 2, I get 2. So I've got my table. Where is the maximum and where is the minimum? So the minimum value is here when x is equal to 1/2. The function's minimum value is minus a quarter. And the maximum value is when x is equal to 2, the function's output is 2. Had I not been careful to include x equals 2, the point where the function fails to be differentiable, I would have totally missed out on finding the maximum value of this function. It's really easy to see why this is so important by taking a look at a graph. Well, here's the graph of this function, x minus absolute value x squared minus 2x, on the intervals 0 to 3. And you can see the minimum value occurs when x is equal to 1/2, and the maximum value occurs when x is equal to 2. And that point really is a place where the function's not differentiable. I mean, that's exactly why I see a corner there. The upshot here is that a point of non-differentiability, a place where the function fails to be differentiable, could very well be where the maximum value occurs. You can think of calculus as a maximum finding machine, and you're trying to find those maximum values. So if calculus fails you at some place, if the maximum finding machine is broken for some particular input, that could very well be where the maximum value is hiding. So you're going to need to check there.